Hi guys, this is it. Last one, 11.1c, hypothesis test for slope. All right, so we're going to do one example with data, one example with computer output, and then we are done with new videos for the year, and you're done with notes. We'll still do work though. All right, so here's how our hypothesis tests work for slope, for least squares regression lines. So we're still doing state, plan, do, and conclude. We're going to start off by stating that our null hypothesis is that our slope equals 0. So there is no linear relationship between whatever x and y are. All right, context, you can have that there. All right, our alternative hypothesis will be that we either have a positive slope, a negative slope, or not equal to 0. Not equal to 0 means that there is a linear relationship. B greater than 0 means there is a linear relationship as well, and it's positive. B less than 0 means there's a linear relationship as well, and it's a negative slope. All right, we should state what B is, so the true slope of the least squares regression line relating y and x in context, and we should state an alpha value. If they don't give us one, 0.05 usually works. And this alpha is not the same thing as the least squared regression line, y-intercept alpha, different alphas. All right, I may have just confused people there. All right, so we are doing a t-test for slope or a t-test for linear relationship. Either one of those is fine. I usually just like to use slope because it's a shorter word, but it really is a t-test to see if there is a linear relationship or not. Our conditions are still the same as before, liner. So we want our scatter plot to look linear and no residual pattern. Our n to be less than 10% of the population. Our histogram for normal of the residuals to be not strongly skewed and to have no outliers. Equal standard deviation, the residual plot should show an equal amount of scatter around a horizontal line at y equals 0 or at resid equals 0, in other words, the x-axis, and we should have a random sample. All right, to perform the test, so if you have the actual data, you put them into lists, and then this is lin reg t test under our test menu. All right, we'll record the t, the p value, the degrees of freedom, and it gives you everything else. Like it gives you the intercept, it gives you the slope, it gives you r, it gives you r squared, it gives you lots of stuff there. So there's lots of good stuff you can write down from that. Or, the more likely of the two things, if you're given the computer output, you're just going to record the t and the p. All right, it's in the chart. All right, those last two columns of the chart, that's what those are. There was always that t column and that p column. Well, that t score and that p value are what you want. All right, and again, it's the one, keep going over from the x variable. So last time we used the standard error and beta, so just keep going over, it's the next two. All right, we do need to write down our degrees of freedom. And if p is a one-sided test, so like if you're doing that just greater than or just less than, we're going to divide the p by 2 because that p that is there is for a two-sided test. So it's for the not equal to is the p value that's given. So if we have either one of these, we take that p value and we divide it by 2 because it's a one-sided test instead of a two-sided test. All right, and then same thing as before. If p is low, reject the hoe. So if we are rejecting, we have significant evidence of a linear relationship. If p is not less than alpha, we fail to reject the hoe. We do not have significant evidence of a linear relationship. All right, so here we go. Following table gives serving speeds in miles per hour of 10 randomly selected professional tennis players before and after using a newly developed tennis racket. So we've got the old ones and the new ones. So the old ones will probably be the x. The new ones will probably be our y. Well, I guess we don't even need predicted here. It is just the y that they get from there. Is there evidence of a straight line relationship with positive slope between serving speeds of professionals using the old and new rackets? All right, so let's start by defining what our beta is. So it's the true slope of the least squared regression line relating x old racket. Is there a C in racket? Yes. Serve speed and y new racket serve speed. All right, our null hypothesis is that our slope is 0. In other words, it's not linear. Our alternative is that it's positive. So beta is positive, greater than 0. So remember, that means that this is a one-sided test. And they didn't give us an alpha, so we'll use 0.05. All right, so we are doing a t-test for linear regression or for slope. Our conditions, L, we need this to be linear. All right, and we need the residuals to not have a pattern. So we'll pull out our calculator on stat, edit. There's the two datas and lists. All right, if you want to do the linear regression with it, so it will already have the residuals somewhere saved, then we just do the linear regression quick. All right, so there's our line right there. We can write down any of that if you want. Down here, we might write it later. But now the residuals are saved in resid. So if we go to stat plot, let's see, we just go to number 1 here, turn it on. We select the scatter plot. We select our 2 graphs, and we're zoom 9ing. So there's our scatter plot. So that definitely looks pretty linear to me. All right, we also want to check the residuals. So we go to stat plot again. We're going to turn that one off. And I've got the other stuff saved in, I think, there we go, with number 3. I'm going to turn this one on. We've got L1 and resid. Okay, cool. Zoom 9 for these guys. And there's our scatter. Looks like maybe there is a little bit of a pattern there, but this guy kind of throws it off. So I guess we're okay. So we definitely have a linear scatter plot. And we're going to say that there's no obvious pattern of the residuals. All right, I, independence. All right, well, each tennis player is obviously independent of every other tennis player, or n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. N equals 10 is definitely less than 10% of all tennis players. I guess we probably should say pro tennis players because there are the word pro in there. And all right, the normal condition, we want to look at the histogram of the residuals. So we go back to our stat plot. Let's see, I'm going to turn off the residuals here. And back to stat plot. I've got it saved in number 2. I'm going to turn this one on, and it's just the residuals, zoom 9. And there's our residual graph. Like, it's a little bit skewed, but it's not bad. All right, so there's no outliers. Oh, and we want to say this is the histogram of the residuals. Residual histogram has no outliers and is not strongly skewed. So that checks out. E, the equal standard deviation. So we had a similar amount of resid above and below resid equals 0 for each x value. And ER, we're going to assume that there was a random, oh, there we go, randomly selected. All right, so random sample stated. Done. All right, so there's our conditions all checked out. Whew. I know, it's a lot of work. Usually they give us all that stuff, though, and we don't have to make it. So usually it's a lot faster. All right, so since we are using the data, linreg t test is what it's called in our calculator. So let's go to our calculator. And stat, over to test. It's down towards the bottom, so I'm just going to go up, and there it is, F. Our data is in 1 and 2. Frequency, we're just going to always leave as 1. Our alternative hypothesis, let's see, we wanted a positive slope is what we were looking at. So we want greater than or equal to 0, or just greater than 0, and calculate. And there's everything we want. Oh boy. So T is 5.767. The p-value p-value was something very small, it looked like. See, it's got this e -4, so here it is, p-value 2.1 times 10 to the -4th. So definitely a very small p-value. Our degrees of freedom is 8. And it gives us all the other stuff there too. So if we do want the line, which we probably are going to, and it sees we can scroll down here with the little arrow there. Like there's our A, there's our B, there's the standard deviation of our residuals. So we want to probably write all that stuff down. So our A is 9.15. Our B, our slope. And again, the reason I'm writing this down is most of the time there'd be more to this problem. So 0.992. Usually we'd have to do this first, actually. Our S is 4.38. Standard deviation of the residuals, 4.38. That's the S. R squared is 0.806. And R is 0.8978. So 898 would be probably fine. All right, so that's a strong R. All right, so there's a strong relationship here, and our p-value is very low. So since our p-value equals 2.1 times 10 to the -4th, anytime it's in scientific notation, it's going to be less than our alpha. All right, we reject the HO. And our HO was that the beta equaled 0, that there was no linear relationship. So that means we have evidence of and it's not just a positive linear relationship. Positive linear relationship between old racket and new racket serve speeds. And I don't know if you want to say it's in miles per hour or kilometers per hour. I guess it didn't say here. All right, so we'll just say serve speeds. There we go. Example 1, done. I know, it's a lot of writing. I understand. All right, it's actually easier when they give us the computer printout, which is the next example here. So here we go, a next example. And last example, I think, for the class this year in the notes. So infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ scores. Researchers measured the length of a cry in seconds as a response to a uniform stimulus for a random sample of 38 infants. Later measured their IQ scores at the age of 3 years old, because you can't really test an infant's IQ score. Below is the computer regression analysis of the output. All right, so we've got cry time, that's our X. IQ is our Y. This is our slope right here. This is our standard error and beta right here. This is our A right here. This is our T right here. This is our p-value right there. Here's our R squared, 0.207. That's not very strong. All right, and this is our standard deviation of the residuals. All right, so we've got everything we want. And so we got 5 questions here, 5 parts, part A through E. So this is kind of like a normal free response question with linear regression. So what is the equation of the regression line that predicts IQ as a function of crying time? So for part A, predicted IQ equals A, 91.27. This is positive, so plus 1.49 times cry time. Done. B, interpret in context the slope of the regression line. So we're going to say that our slope, which we usually use the letter B for, is 1.49. So that means for each increase in, and I remember, let's see, we used to write this as 1.49 IQ per 1 cry time. Remember, we used to write that out every time. We always put it over 1 of whatever the X was. So for each increase in 1 second of cry time, we predict, on average, an increase, it's positive, in whatever our Y stands for, IQ, by 1.49, and we put some units here. In this case, it's just points. All right, so there is what our slope means. C, what is the meaning of r squared in the context of this study? All right, C, r squared, the coefficient of determination, is 0.207 or 20.7%. That means 20.7% of the variation in y, which is IQ score, can be explained by a change or just by cry time in seconds. All right, so a certain percent of the variation, maybe 20.7 or 21%, but that's, close enough, of the IQ score can be explained by cry time in seconds. Cool. D, give the value of the correlation coefficient. All right. Correlation coefficient is R. And it's going to be the square root of that, the square root of R squared, 0.207. And it is going to be positive since our slope was positive. So it's going to stay positive here. So we just need to take the square root of 0.207. So second, quit that. Second square root, 0.207. There we go. 0.45. All right. So that's just the value of it there. So, I mean, it's positive. And we could say that this is a moderate. All right, again, below 0.3 would be weak. 0.45 is somewhere in the middle, so it's not bad. All right, we could do other things here too. We could plug in cry times to predict IQs and things like that. They could give you one data value and ask for the residual, and you could do actual minus predicted for residual. All that sort of stuff is all fair game for these type of questions. But the last one it's asking us to do here, part E, perform a test of significance for the slope of the regression line. All right, well, we're gonna need more room and we're gonna need some more graphs. So there's the more graphs we need and there's the more room. So we're doing a test. So we need to state what our beta stands for, is the true slope of the least squared regression line relating cry time, which was our x, to y equaled IQ score. All right, and our null hypothesis is always that the slope is 0. That means it's not linear. Our alternative hypothesis, and it just says perform a test of significance. So we just want to know, is it a line? So is it not equal to 0? All right, could be a positive line, could be a negative line. Looks like it's a positive line for this guy. But we just want not equal to 0. And we're going to use 0.05 for our alpha value. All right, next up. So this is a t-test for slope. You can put beta here if you want, or for linear regression. L, so we've got linear. Yeah, sure, good enough. Residual, no pattern. All right, so linear least squared regression line and no residual pattern. That checks out. Again, I'm just going with a liner here. L-I-N-E-R, our condition. Independence. All right, so did it say what our sample size was? It did, N was 38, which is probably less than 10% of all infants. And every kid is going to be independent of every other kid. N, normal. We're going to take a look at our histogram here for the residuals. I mean, we may have an outlier, but we're not sure if that's an outlier. I mean, the IQR is probably going to go from there to there, so I don't think that would end up being an outlier. So the residual histogram, just because there's a space there does not mean something is an outlier, is not strongly skewed. and has no outliers. Check. E equals standard deviation. So if we look at this graph, like we've got about the same amount above here as we do below. So we have the same amount above and below resid equals 0 line. So that checks out. And R, somewhere we had a random sample. There it is. R is always the last and the easiest one. Random sample stated. Check. All right, so all of our conditions check out. So now we're coming over here and we want to do our test. Guess what? There's our T, there's our P. All right, so our T score, 3.07. Our P value is 0.004. Now we have to check to make sure, is this a one-sided test? Researchers measure, I mean, we said two-sided here, but I just want to check to make sure. Measure the IQ scores of 3-year-olds below is the computer output. More easily stimulated than others. This may be a sign of higher IQ. Researchers explored. All right, we might actually want to do, I might have put this wrong. We might actually want to do greater than 0 because we want their IQ to be increasing because we said higher IQ here. So we might actually want greater than. So what we want to do, since it's one-sided, we want to divide that by 2. 0.002 is what we get for our p-value then, since it's just looking at the above side. All right, I don't really have anywhere for conclusion down here or anywhere, so I'm going to go over here to conclude. So since our p-value equals 0.002, which is less than 0.05, which is our alpha, we reject H0, which is that beta equals 0. We have significant evidence of a positive linear relationship between cry time and IQ. I mean, it wasn't super strong, but we have evidence of this linear relationship still. All right, and we are done. Quite the test, I know, right? But this part, the do part, was super easy, right? We just had to read off the T from here. See, T, boop, there it is. And P, there it is. And it's always those two. Those are the only two that we want. And since it was one-sided, we have to divide it by 2. All right, and I did go back and see that they wanted it to be higher, so we want positive slope. All right, and that's it. And this is probably the longest video of the year, but we are done. That is it for statistics. Turn in your notes, get working on the homework, and you guys are almost there, guys.